What's going on, guys? So today we are going to be working on our roller coaster uh, quantitative investigation here. All right, so the main objectives are to compare and contrast mechanical energy and kinetic energy, and then example the relationship among kinetic energy, gravitational potential energy, or GPE, or just GE, and then total mechanical energy. That's exploration part two. We may get to part three. We'll kind of look at that, but that would be explain how changing the level of zero potential energy reference line affects an object's motion and total mechanical energy. All right, so part one, explore this thing for a couple minutes and determine if there is any relationship between kinetic energy and potential energy during a roller coaster ride. So when you click on the link, it takes you to the virtual investigations. So with this, all right, we have our red, we have our as for kinetic, green for potential, and blue for total energy, which is our mechanical energy. So I believe, let's see, if we can restart, we can change the height of a hill one. We can change the initial velocity. We can say that right up here, that's not zero potential energy. Zero potential energy is going to be all the way down to the bottom. Why is that? Well, because potential energy or gravitational potential energy is equal to an object's mass times gravity times height. So right down here, height is zero, so the potential energy of the object is zero. This is gravitational potential energy. All right, that's gravitational potential energy. Where's my little eraser guy? Cool. So if we then hit start, what do you think is going to happen with the velocity? Yeah, it's going to increase. Boom. Okay, now what I want to show specifically here is look at the total energy in the blue, look at the red, and look at the green. As soon as I hit start. Blue does not change. What did change? Potential energy decreased, kinetic energy increased. But the blue did not change. So the total energy, or what we would call mechanical energy, how do I get to the, no? Where the heck is, how do I get to the, there we go. Sorry about that. So mechanical energy, or our total energy, is going to equal the potential energy at any point, which has to do with the changing of height, because your mass should not be changing, gravity should not be changing, so it's really going to be based upon your height or location, and that is going to be potential energy, right? So right now, potential energy is zero because the height is zero, so that means that all this mechanical energy, all right, should be the same then as your kinetic. So at the very, very bottom of this roller coaster point, all right, we are at our maximum kinetic energy. So 0 plus kinetic will give us potential energy down here. At the top where we were not moving, where V was equal to 0, we had 0 kinetic energy. And how do I know that? Well, if again I go back to, where's my eraser? Back, there we go. So we can go back and look up top. Why up there we get the fireworks off. So let's restart one more time. Just get fireworks off. Thank God. Okay. So when you start, velocity 0. Now height I have all the way down here at 0. Now if I bring this up, all right, the height will be the same height as the initial hill. Now that's why they're saying like, oh, the height's going negative. even though, right, that would be more so displacement. So velocity 0 at the top, 71 meters per second at the bottom. Now our height should be 260 at the top, 0 at the bottom with our 0 potential energy. So if potential energy has to deal with our height, the object's mass and gravity, and what do you notice here? Where's my eraser? What do you notice here on the energy graph? As the speed increases, what happens to kinetic energy? It increases. Very good. So with this, that was going to then tell us that kinetic energy definitely has to do with something moving. So we still have the object's mass. Now, the equation for this is kinetic energy is 1/2 mv squared. So at any single point on a isolated system, like in this roller coaster here, the potential energy at any point plus the kinetic energy at any point will give us our total energy or our mechanical energy. And that's going to stay constant. All right, that's going to stay constant for us, that mechanical energy. So once we can figure it out at one point, we're good. We should be able to then determine, all right, a few different other things from there. All right, so roller coaster, okay, we explored it. We had a backwards L, initial velocity is 0, set mass to 100. All right, and then set 0 potential energy across the bottom of the track initially. That's what they meant right down here. Mass is 100. They didn't tell us exactly what to set the hill height to, but we do. Okay, and observe what happens. So again, as I said, the total doesn't change. Gravitational potential energy decreases as the height decreases, but the kinetic energy increased. Okay. So allow the roller coaster to move again. Pause the simulation at several more representative points according to the car's height and speed at each point. So pretty much bring it up. Pause. Okay. Height, instead of it originally at 260, we're at 236.8 and the velocity is 20. Play. Pause. Do it as many times as you need to for here. All right, so we have our height, we have our speed, and it asks us to calculate the kinetic energy for each speed listed in Table 1. All right, so again, to do that, you're going to use this equation. You're going to use this equation, 1/2 mv squared. Okay, and then as the car moved, what did you observe about the total energy? Well, again, like I said, the blue box here. Total energy didn't change. All right, total energy didn't change, it remained constant. What did you observe about the car's speed as it moves along the horizontal section of the track? Okay, so the horizontal section. What about the speed, the velocity? Does it change? No, so we're assuming that it has to be frictionless at that point. Contrast the roller coaster's total mechanical energy with its kinetic energy during the motion. Explain what might create the difference. So the total mechanical energy, the blue, doesn't change, but the kinetic energy did. So what is the, as red is going up, what do you notice? The height's decreasing, but what is increasing? Yeah, your velocity. So kinetic energy, yeah, big time, has to deal with our velocity. And then exploration 2, gravitational potential energy and kinetic energy. Construct a simple course beginning with a downhill section and an uphill section. Set the height of hill 1 and hill 2 to the same value. Okay, set 0 potential energy to the lowest level on the track. The bottom of the valley between the two hills, set initial velocity to 0 and mass to 200. Okay, so mass to 200. All right, we got to restart. Okay, mass is this. We have our initial velocity. No, I'm sorry. Mass was supposed to be set to 200. So if mass is 200, okay, can't get this to go just there. It's close enough. Okay, what else did we need? We needed lowest level of the track. Okay, set hill 1 height and hill 2 to the same value. So let's just say, let's bring this, you know what, put it at 180, and then hill 2. Let's also bring it to 180. Okay, and then anything else? Okay, go again. And then you'll hit restart, go again. This time, pause the car as soon after you select go. Record the car's height, speed, and description of the car's position at this point in table 2. Allow the car to move again, pause it to several more representations. Look for each point, record the car's height, speed, and a description of the car's position in table 2. Okay, so you would then change, list the height and speed. So we need height, we need speed, description of the car's position just after the start. Potential energy. Well, potential energy should just be mass times gravity times height. Now we can use just 10 for gravity instead of the 9.8 just to make the numbers come out a little nicer looking and clean. So that would be how you can calculate here for potential energy and your kinetic energy. And then again, allow the car to move again, pause it at several different points. For each point, record the car's height, speed, and description. So then we do start, pause, all right, record velocity, record height, do the calculations, start, pause, same thing, start, pause, same thing, start, pause, same thing, start, pause, same thing. I would definitely use the bottom as one of them. Now as it goes up, now your height, velocity, height, velocity. Now I don't think I can take this and move this to where exactly I want it to be, but maybe on parts of the way down, like if you can get it to try and be like right, let's say here, you can get it to be, pause it at one of these lines on the way down, right? And then try and hit pause almost exactly, as best you can to these corresponding parts. So I would say like right here on the start, here, definitely at the bottom, here, and here, and that should be 1, 2, 3, bottom, 1, 2, 3. All right, so we'll need, you can, use a couple more here, a couple more points, but definitely try and get those 7 points for sure if you want to do just right at the top and almost just at the top here. All right, you're not going to want to do several points at the bottom because it's not going to really do anything for us. Okay. And then from there, calculate your potential energy, calculate your kinetic energy so that, again, using the equations that I listed here, that's what you're going to need to do. And then you are going to, let's see, go back, no. Compare and contrast the car's potential energy with kinetic energy. Again, what you should see, guys, is as kinetic increases, potential decreases. So if we get rid of all that and hit restart. Again, look at the blue. Blue's value, solid, ain't changing. Look at the green. As that goes down, what increased? The red, which is your kinetic. Now, at the very, very bottom, we have all kinetic because the height is 0. Now, what do you think is going to happen as you go up? Yeah, that kinetic energy is changing into potential. Why? You're increasing your height and your speed is decreasing. So as the velocity decreases, okay, and you're going upwards, you're increasing the height, potential energy increases. But again, if you took these two values and added them together, they are going to do or should equal this number, the mechanical energy. So usually the easiest way to calculate mechanical energy is if you know what the mass of the cart is, which we have right here. It should be 200. I just couldn't get it to be right on it. And the height, mass times gravity times height. Now, since it's not, our velocity at the very start of any roller coaster is initially 0, that means at the very, very top point, okay, at that very top point, mechanical energy is going to be equal to all of potential, all right, just potential. Now, granted, we understand that mechanical is potential plus kinetic, but if kinetic is 0 up here because the velocity is 0, well, then mechanical energy is going to equal the potential. So that's usually the easiest way to figure out this dude. And then, as the height changes, potential is going to decrease, then kinetic energy will increase. So we definitely want to make sure, all right, we know that. All right, that's a little like kind of not a cheat code or anything like that, but it definitely makes everything a little bit nicer, a little bit easier. Okay. Study your data, state how potential energy, kinetic energy, and total energy are related. All right, so yeah, basically I just said it. So mechanical energy and potential energy, all right, at any given point in a closed system are going to equal the mechanical. At the maximum height and where the speed is 0, all energy is total potential, right? So potential energy is max at the top and it's minimum at the bottom. And if the height is 0, then potential energy is 0. And if kinetic energy is 0 at the top, right, at the bottom where the height is 0, all of that energy is now converted to kinetic, right? Kinetic energy of motion. And yeah, we're probably not going to necessarily get through. I'm not going to have you guys, I don't think, do part 3. So that's the kind of idea and the gist of like kind of this baby exploration. All right, main things that you definitely want and need to know: at the top where the velocity is 0, all of your energy is potential. So if you know these 3 things, you can then solve for this. This number then won't change at all. Okay, so let's just say the answer was 100, then it'd be 100 here, 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 all over. All right, for mechanical energy. Now the other things can change. Right? Your potential will change because you're decreasing your height. So that is going to decrease, but what will increase is the kinetic energy. Why? Because our speed is increasing. Where the height is 0, all right, all your potential energy then is 0. It's converted all to kinetic. So there's a way that you can, which we'll probably look at in the next day or two. If you know mechanical and potential energy right here, right? Let's just say the answer is 100 joules, because energy, unit for energy is joules. So if it's 100 joules at the top, and that's all potential. At the bottom here, potential energy would be 0, and the kinetic would be 100. All right. If you already know what the object's mass is, and you know kinetic energy is 100, you know what the mass was, okay, you can rearrange this to solve for V. Pretty simple. Okay, so you multiply both sides by 2, so it should be 2ke. Got to divide, right? And that would leave us with mv squared. Divide both sides by m, and then that would equal v squared, and then you square root it to get the v. And that's how you can figure out what the velocity is down here at the bottom. Okay? All right, guys.